Hello everyone, it's immense pleasure to be here on this wonderful occasion, International Conference on Holography meets Advanced Manufacturing, and share my research work which we done in our laboratory. I am Jagadeesh Suriyaprakash from South China Normal University, and we are working on nanophotonic functional material and devices. Here I am going to share a few of my laboratory technique which we use to manufacture advanced nanoscale material by photon, that means it's laser. So go to the next slide. So this is the outline of my talk, motivation, background and methods. Here I'm going to describe about synthesis of carbon nanodots and ligand hybridization and fabrication of versatile gold nanostructure from one-dimensional gold nanowire and advanced 2D polymeric photonic structures, and along with the result and the discussions, and finally conclusion. So motivation. Nanostructures and nano devices have become a key component in optics, optoelectronics, biomedical and biomedical detection, and etc. Versatile photonic structures at the submicron level are in great demand due to the exponential development of micro-nanotechnologies. This has piqued the interest of researchers in developing efficient processing as well as fabrication methods for their cutting-edge design. So in this context, we use femtosecond laser and continuous wave low one photon direct laser writing techniques, so which will assist to tune the structural and surface property of the 0-dimensional, 1-dimension and 2D nanoscale materials. As I said before, with these methods, intricate designs can be produced in a single step by adjusting the laser power without the use of laborious post-processing operations. So here I give the two picture example is a laser induced new structure or the material, and this is the classical example of laser induced periodic surface structures. So when the laser interact with liquid phase or solid phase, owing to their parameters and also the precursor, we can manipulate the surface structure and also the internal structure of the material from one to another dimensional nanoscale material. And here we come about the laser induced periodic surface structures. When we use the wavelength with the dopant material, the subwavelength of the periodic surface will create. So this is a well-known phenomena. So I'm mainly focusing on in this talk is about these laser induced new structures and the new material. And coming to laser induced chemical transformation, this is one of our recent work, and another example is laser induced splitting phenomena. This is also a recent work which was done by our graduate student. And when we talk about the advanced material manufacturing, of course we cannot ignore the carbon materials and their functionalization, because carbon materials has a wide range of application from biological, chemical, optical and electromagnetic field. So in day-to-day life, and many methods has been carried out from top down to bottom up. Laser induced carbon material is one of unique advantage. So I am also going to talk about how we did carbon nanomaterial from our experiment. So the methods, the first example is synthesis of carbon nanodots and ligand hybridization. So here is a typical schematic diagram of how we design the experiment. So here is the femtosecond laser and attenuator and reflector. This is the optical path and focus the lens. So this is the cuvette. So this is the cuvette we filled with initial graphite, like a carbon, not a graphite. The source is come from the biomass. So then we put into the water solution. Then we increase the different power of the femtosecond laser. Then we obtained a different material, like for example here we got the graphene, few layer graphene from the graphite and the DMSO and the SDS source with particular amount of laser fluence and time, and we change the chemistry of the precursors. We use the same graphite as a initial material, but we change the chemistry in it. When we add oleolamine into the solution, then we finally got the carbon nanodot, which has a fluorescent property. So one can play around even if we know the method how to design the material. For even when we do for it is a two-dimensional graphene, and this is the carbon nanodot. It's come from the same source, so we just play little bit parameters. So this is another example here. So after we synthesized, we want to some part of the material which is not suitable for some application, for example biological application. We need to make it into biocompatible or change the dispersibility. So how to do this process is but mostly conventionally they use by ultrasonic or chemical transformation or more agitation or thermal heating, but it will also affect the material itself. So but laser induced ligand hybridization process is a unique technique. It don't give any adverse effect. It just make the surface to assist to the another surface surfactant molecule to anchor into that the initial material what we took. So the FTIR spectra of initial, like the precursors oleolamine and carbon nanodot para-aminophenol. So this is the thing, and here is the photoluminescence spectroscopy. One can see that when we change the ligand from precursor to the another one, so we can get a distinct peak. So we confirm that one. So this is a very robust technique to make the ligand hybridization process by the laser assisted experiment. Then we also change the structural morphology characterization. As I told before, this is the graphene and this is the carbon nanodot, and from that we also make a combination of these two, which is supported by carbon nanodot on the graphene structure, so which is a hybrid material which mostly utilized in sensing process and electrochemical capacitance and etc. So and these are the characterization study. We further characterize to what is really going on to derive the mechanism of formation. So these are the XRD pattern and UV and Raman spectroscopy, and this is the typical carbon based material structures and their application towards the optoelectronics. So here is the formation and the ligand hybridization mechanism. So when the laser is interact with the graphite initial material, if we increase the time, so we get the graphene. When we increase the power and reduce the time, we get the carbon nanodot. so which is highly governed by high surface energy and cavitation, bubble formation, and Coulomb explosion. So these are the phenomena which mostly exploit in this experiment. And how the oleolamine converted into para-aminophenol ligand hybridization process is mostly done by surface functionalization via light assisted and part of photothermal effect also. So coming to the next section, next example of fabrication of Westlake gold nanostructure from one-dimensional gold nanowire here. So fabrication of Westlake gold sorry, excuse me. The same experimental setup. Here we just change the precursor material as we want. So we took the initial material as a gold nanowire, which is one-dimensional structures, and we can see the gold nanowires are all supported by the gold nanosphere, like grapes on the tree, like a grape bunches, not like bunches, but it's a kind of periodically like array of structures along with the nanowire itself. So so here is the when we increase the power from 30 milliwatt to 90 milliwatt, so we can see step by step how the nanowire turn into a nanosphere structure, and how the two structure is coexisted in one part. Like here is the initial state, and these two are intermediate state, and this is the final state. And here is the mechanism of phenomena which we done by simulation experiment to know where and how it will break the bond between two adjacent atom of gold nanowire. So initially we have this, and more surface energy taken by the gold nanowire, and as usual it's tend to form low stabilization energy, so it's break up little bit, then further and further, so finally it attain the gold nanosphere. For example, here we can see when we change the time of 15 minutes and the power of 19 millivolt, we get gold nanosphere. When we change the time of 1 minute and 50 milliwatt, and we get gold nanorod. When we change the time 100 minutes and 30 milliwatt the power, we get the gold nanosphere along with the gold nanos wire. And when we change the 30 second and 70 milliwatt of the power, we get the gold nano tadpole structures. So, and here is the FDTD simulation of the field effect. So from this method only you take one precursor and you change all the little bit, play around with the time and the power, so we get a versatile of structures. So this is another typical example. So here is the formation mechanism, same like when the laser interact with the gold nanowire. When the time increase and we get low power, we get nanorod and large size nanosphere. And when the constant time increase, we keep this time constant and we increase the power, then we get the ultrafine nanosphere. So finally we come to the advanced 2D polymeric photonic structures. So here is the full experimental schematic diagram. First we spin coat the polymer, and this is the whole optical setup. Then this is the laser scanning direction just by changing the power, and this is the precursors and after a solution of UV spectra, and here is the formation mechanism. So in this case when we increase the fluence, laser fluence from 0.08 to 14.32 millijoule per micrometer squared, so one can see the hole. Then we get the little rod inside like anti-ring. Then after that we only get the dot, like a dot, then again like a dot. Then after that, while we increase this one, we get a donut structure. So let me explain what is going on in this structure. Actually, this is the positive photoresist. So positive photoresist means once you expose, then you develop, then it should be dissolved, and you get the what is the pattern. So here the photoresist act till here as a positive, but here the center beam acts of the laser, which create the chemical transformation of the positive photoresist into a negative photoresist, and it grow bigger and bigger. But here, after some extent, the center beam of the laser energy is, when it's too high, it burn the center part and it create the nano donut structure. The structure itself, there is not completely a hole, but it is a little deposited. Actually, we tried our microanalysis. We interestingly find that structure is as a laser induced gravity structure, which is inside. So here is the array of structures which we developed from that experiment which I shown before, and these are the experimental details, and here are the functional group changes, and we want to tell why and how it forming from positive to negative photoresist by this experiment. So here is the formation mechanism. So it totally it's controlled by the chemical transformations of the polymeric structures, and also a laser ablation process. So we fabricated the novel material by simple laser techniques which alter the surface and structure of their counterpart, and it has been discovered that the chemical transformation and ablation effect plays a significant role, and this work sheds a light on the development of simple and effective micro and nano optoelectronic device fabrication method, as well as characteristic tunability. Of course, I rush to finish within the timeline, so I am welcomes to your questions and everything through mail or whatever the media you can contact. So I acknowledge my funding agencies and my collaborators and my family members and my wife. So finally, thank you for your kind attention.